Hello, physics class. We're going to start a 1 week long crash course in magnetism. So that will divide into three little pieces. First piece is magnets and magnetic fields, and that's this video you're looking at right here, right now. This groovy video you're looking at right here, right now. So for starters, I hope you guys are all happy and healthy. Hell, I hope you're all happy and healthy. You know that's supposed to say hello above that? I find that greatly amusing. I'm not going to fix that. Hello, I hope you're happy and healthy. If you are, if there's something going on that I need to know about, please don't hesitate to reach out to me. And I mean, if that's related to physics class, if it's related to school, if it's a tech issue, if it's something bigger and more life-shattering than those. I'm here to be supportive, okay? One way I can do that is to show you a brief video of me juggling back when I was carefree in pre-COVID days. Here it is. Watch closely. Oh, that didn't work at all. Let's try again. I like that because you can almost not see my hands. I find that that entertaining. Okay, next slide. Okay, so here's the objectives for this little section here. For given situations, predict whether magnets will repel or attract each other. That's not hard. Then the second one is describe the magnetic field around a permanent magnet. Also, not too hard. And then finally, describe the orientation of Earth's magnetic field. So, all simple things. So for starters, we're going to do a brief introduction to magnets. What are magnets? So magnets, you can see here this little physics prodigy who's experimenting with magnets. Magnets, I went through a time when I was probably in college, I guess, and studying physics where magnets felt like the more I knew about them, the more mysterious they were, and I kept slamming my head against the question, what in the world are they? Or how in the world does it work? If you find yourself slamming your head against that same question, here's something you should bear in mind. It works kind of like gravity. There's a force that acts at a distance. We don't really dig into, we just accept gravity. We've lived with it long enough that it's okay for us to understand that if I drop this pen off the table, it will land on the floor. It just happened. And it doesn't blow our minds. For some reason, magnetism does, because it just seems a little bit different. But really, in physics, there are only 4 forces. I mean, I don't mean in physics. In our universe, the place that you and I live and love, there are only 4 forces. There's the electromagnetic force, and that's part of what magnets are. And then there's a gravitational force, and then there's a strong nuclear force and a weak nuclear force, and we're not even going to talk about those last 2, probably. So that's it. So if gravity doesn't cause you to lose sleep, magnetism shouldn't either. There are a lot of similarities. So we're just going to have to embrace the mystery. Okay, on magnets, they seem so mysterious because it's sort of odd and what's making things pull together. And I can only tell you it's the electromagnetic force, just like what's making me not fly off my chair is the gravitational force. So in this week, whenever we refer to magnets, we're going to think of them as bar magnets, just a straight line. So similar to this straight line here. We're going to ignore the ball and the horseshoe. Basically, everything in this thing, including the Earth itself, can be kind of modeled as a bar magnet. And a bar magnet has one end that's just referred to as the north end and one end that's referred to the south end. And strangely, if you cut a bar magnet in half, this end won't be all north and this end won't be all south. If you cut it in half, this one will have a north end and a south end, and this one on top will have a north end and a south end. And if you cut each of those in half, all those little smaller magnets will have a north end and a south end. They'll all be oriented the same direction. If this is north here on this little yellow magnet and this is south, And no matter how many times you cut it, the south end will be toward the bottom and the north end will be toward the top. But you can cut this down into sliver size bar magnets, and they will all have north and south ends. And then for uses of magnets, it's really pretty phenomenal how useful and how used they are. Anything that's electronics and magnets dovetail together. That's the same force. If you have generating an electric current, you're also generating a magnetic current, and vice versa. So if you have a magnetic force that's okay, I'm getting ahead of myself. I'm maybe getting a semester ahead of myself, and we may not get into it too much, but your computer that you're viewing this uses magnets. Magnets are used in industrial settings to lift heavy weights. Electromagnetics are. They're used in the healthcare industry for magnetic resonance imaging, or MRIs. Really, the thousands and thousands of uses of magnets. So this is something that that even if it feels like something you don't really understand at a gut level, we can still use it, even without feeling like our guts are comfortable with it. Okay, so here's something you should know about bar magnets. Like poles repel each other, and unlike poles attract each other. So the North Pole and the North Pole on two bar magnets will repel, and the North Pole and the South Pole on two bar magnets will attract each other. It's similar to what happens with electric charges. There's a lot in common with electricity and magnetism. Okay, magnetic domains. A magnetic domain is it's a region composed of a group of atoms whose magnetic fields are lined in the same direction. So maybe this will make sense over here. Let's say that we have some random piece of iron, and we're going to picture all the atoms in this random piece of iron as little bar magnets. And if that random piece of iron is not magnetized, if it's unmagnetized, the bar magnets their orientations are random, so they'll offset each other. So you can't really notice a dominant magnetic domain here because there isn't one. It's not magnetized. Now that same iron bar, if you could orient all the magnetic fields inside this iron bar in the same orientation, then you would have a magnetized iron bar, and you would have a north end over here and a south end over here on this thing, because all the little domains point one direction. So the movement, here's something you should bear in mind. The movement of electrons is what creates a magnetic field. So like I suggested earlier, electrons moving generate a magnetic field. So since we know that electrons are in constant motion, that means every single atom has a little bit of a magnetic field attached to it, including atoms that make up of you and me. So it's just that our atoms are all unmagnetized. They're all pointing in random directions. The magnetic orientation is not aligned. So unmagnetized domains have a random orientation. Domains can become aligned and become magnetic domains. So that's what is going on in the lower image there. Okay. Some materials can be made into permanent magnets. So if we had some piece of iron, it would be possible to orient those domains into a consistent orientation, and they would, as long as they hold that orientation, that would be magnetic. So I'm backing up one slide. If we could take this and convert it to this, that may remain permanently magnetized, like this little quote here suggests. So, okay, and if we had time together, we could talk about the ways that that's done, and how sometimes it's easy and sometimes it's hard depending on what you're magnetizing, and how sometimes those permanent magnets will slowly degrade over time to become demagnetized, and others will remain magnetized for a long time. Okay. Now, magnetic fields, it's just a region in which a magnetic force can be detected. Here's what you need to bear in mind. When I use the word force, I'm not using it like Obi-Wan Kenobi does when he just tells people to use the force, Luke. I mean something specific. I mean a physics force. So we know force equals mass times acceleration. That's not helpful here because we're not taking a massive electrons, and we're not measuring the acceleration of the electrons. But force is also something that can do work. So if you can remember the definitions of work, if you can cause something to move, that is an example of work. So if force is the movement of some mass, okay? So simplified form. So a region in which a magnetic force can be detected is a magnetic field. And a magnetic field is a vector quantity, which means that it has both magnitude and direction. So it's going to have an arrow pointing what direction that force is being applied, and a number, how big a force it is. Is that magnet strong or weak? And is it pulling or pushing, or pulling off to one side or another? And that magnetic field is represented by the letter B. You want to know why? Me too. I don't know why, but it is historically. Okay. Magnetic field lines can be drawn with the aid of a compass. Let me show you what I mean by that. This image here, we've got a bar magnet, and it's surrounded by iron filings. And notice those iron filings just trace out. They fall into this crazy pattern of emanating out from one side and forming these loops and pointing back toward the other side. It happens on the top end and the bottom end of this magnet. It actually happens in 3 dimensions in this magnet too. So it's that magnetic field, if we could somehow do this in space and have them, well, in space they would just slam into the magnet. But if we could somehow do this where gravity weren't slowing these down, the iron filings would be literally coming off the page right here and pointing off this direction and then entering the page over there. Notice what the compasses are doing too. So you've got 7 compasses lined up, and the compass arrows are lining up in the same orientation as the iron filings. They're pointing away from this end and then getting kind of flattened here where it's parallel to the bar magnet, and then pointing directly back at that end. Iron filings and compasses will align with magnetic field lines. The direction of the magnetic field, B, is defined as the direction that the north pole of a compass points. So it's kind of hard to make out on this graphic, but the north pole of this is pointing this way, so the magnetic field at this location points this way. Here the magnetic field is pointing that way because the north pole is pointing that way on this magnet. So at this location, the direction of the magnetic field here is that way, directly to the left. Okay. There's one more term we need to know, that's called magnetic flux. So I told you that a magnetic field is going to be measured. It's a vector, so it's got a number and it has a direction. We can look at the direction this way, but we need some way to quantify the number. How big is that magnetic field? And that term is called magnetic flux. Magnetic flux relates to the strength of a magnetic field. So the magnetic flux is defined as the number of field lines that cross a certain area. All right, what I'd like for you to do right now is just take a deep breath, kind of center yourself. I'm going to show you an equation. All right, if you need to press pause, that would be fine. Okay, I think you're ready. There's a formula. Good news is we're not going to use it, but I want you to see it, because this is how you would calculate the strength of a magnetic field. That's it. Phi sub m equals AB times cosine theta. Here's what that means. Phi sub m is magnetic flux. If you're calculating magnetic flux, you take the surface area, which we'll just call A, times B, which you remember is the magnetic field. So times B, and we need to know just the part of that magnetic field that's perpendicular or normal to the plane of the surface. So that is the equation. If we were going to spend time in class going over this, we might give that a test drive a few times, but we're not going to today. I just want you to know that an equation exists to calculate the strength of the magnetic field, and that is called magnetic flux. Now, Earth has a magnetic field similar to that of a bar magnet. You've seen that before, with Earth sitting here and then magnetic field lines emanating, pointing one direction. Okay, so emanating from one side and moving up toward the other side. Now I'm going to ask you a little hypothetical. If the Earth is like a bar magnet, which it is, Which magnetic pole is at the north end, where Santa Claus lives? Look at that graphic.